Hi everyone, and welcome back to the MCAT A series of lectures in physics. In the previous video, I explained in detail what a light wave is, as well as introducing various parts of light theory. This video will instead focus on the propagation of such light waves, that is, the propagation through a certain medium, as well as the propagation from one medium to another medium. This topic is known as geometrical optics. I shall begin by introducing what is known as reflection, that is, if you like, the bouncing of light as it strikes the boundary between two media. Refraction will then be considered, which is instead what happens to the direction of light as it propagates from one medium to another. As the amount by which light is refracted is dependent upon the wavelength of that light, different colours will be refracted more than others. This results in what is known as dispersion of light. I will then consider the criteria needed for all of the light to be reflected back into the same medium. This is known as total internal reflection. I will then look at the reflection of light in the special case of spherical mirrors. Likewise, refraction will be considered in special situations, namely with lenses. I will then look at more complicated types of refraction by looking at multiple lenses, light being refracted through more than one lens. Lenses unfortunately are not perfect at refracting light, and such imperfections, in other words aberrations, will then be discussed. I will then finish with a brief discussion on how human eyes can be considered as a type of lens. As light waves propagate towards the boundary between two media, some of that light goes through that boundary and is refracted, whereas some bounces back, in other words is reflected and stays in the same medium. The amount of light that is refracted and the amount that is reflected is dependent upon the two different media. For example, in the case of mirrors, most if not all of the light is reflected. Reflection, as I just stated, is in a sense the bouncing of incident light at the boundary between two media. Therefore, reflected light does not enter into the second medium, it stays in the medium that it was originally in. There is an important relationship between the incident angle of that light and the reflected angle of that light. This relationship is known as the law of reflection. To understand this, let me draw a simple diagram. Here I have a mirror represented by a black horizontal line, and I have light heading towards that mirror. In the last video, instead of drawing the complicated sine waves for the electric and magnetic oscillations that represent the light wave, I instead used wavefronts. In this video, as we are talking about light propagation, it makes more sense to instead use light rays. Light rays are simply arrows where the direction of the arrow represents the direction of the light wave, the direction in which the light wave is propagating. Therefore, in this case, this blue arrow on the left represents a light wave heading towards the mirror. This light wave is incident on that mirror at an angle θ1 to the normal, and by the normal I mean the line perpendicular to the mirror. According to the law of reflection, after that light ray has undergone reflection at the mirror, the reflected light ray then heads away from the mirror in the same medium at an angle θ2 to that same normal. The law of reflection simply states that the incident angle is equal to the reflected angle. In other words, θ1 is equal to θ2. Just like with an object hitting a wall under conservation of momentum, the incident angle of that ball with respect to the normal is equal to the angle with respect to the same normal that that ball bounces off with. Using this information, we can then consider what happens when we have multiple light rays bouncing from an object into the mirror. In other words, what is the resulting image we would see if we looked in the mirror at that object? To understand this again, let's consider a simple scenario. Let's assume again that I have a plane mirror, which this time I have drawn vertically, and an object on the left. Let's also assume that light is shone on that object, and therefore light bounces off that object towards the mirror. To simplify things, let's just look at two light rays that go from the object to the mirror. According to the law of reflection, this first light ray that I have drawn must be reflected as shown. The angle of incidence to the normal, that dashed line that I have drawn, is equal to the angle of reflection to that normal. Likewise, for this second light ray, we again have the angle of incidence equaling the angle of reflection. What does this mean in terms of what we see in the mirror? Well, the actual image we would see is where these two light rays would meet. However, as you can see here, these two light rays seem to be diverging. They are getting further away from each other as we move further from the mirror. This means that, in a sense, these two light rays must hypothetically meet behind the mirror, as I have shown here. Therefore, the resulting image that we actually see is in fact behind the mirror. Of course, we know that the light rays have been reflected and therefore have stayed in the same media. There is no light rays on the right. Therefore, we say that this image is in fact virtual. Virtual because the light rays are of course not actually meeting here. There are no light rays behind the mirror. For this particular object, if I was to draw more light rays, I would find that all of the light rays would meet virtually at this same point behind the mirror. This is where the image of that object is located. In fact, it is true in general that plane mirrors always create virtual images. The images that we see in plane mirrors always appear to be behind the mirror. That is, plane mirrors create the appearance that light rays originate behind the mirror. This fact is, however, not true for mirrors in general. It is only true for plane mirrors. To see this, let's consider more complicated mirrors like, for example, spherical mirrors. Spherical mirrors can be broken up into two types of mirrors known as concave and convex. The mirror that I have drawn here is a type of concave spherical mirror. Spherical because it composes part of a sphere. If that black curve continued, it would loop back on itself and create a spherical ball. It is a concave mirror because, if you like, the sides of the mirror are caving in on each other. If we instead rotated this 180 degrees, as we shall see shortly, it would instead be a convex mirror. Let us now consider whether the resulting image for a concave spherical mirror is virtual or real. A real image is one in which the light rays actually meet in front of the mirror, not virtually behind the mirror. To do this, let us consider a simple object O. Here, and as I shall do in the rest of this video, I have represented an object by a vertical black arrow. Don't get confused by this. This is not a light ray. This is just an object of a certain height which I've represented by an arrow. The top of that object is the top of the arrow, and the bottom of that object is where I've drawn the letter O. To simplify things, I've placed the bottom of this object at the halfway point in the mirror. In other words, the ground, the blue horizontal line that I've drawn, goes through the center of that mirror on the right. As I already stated, a spherical mirror is called a spherical mirror because if I continue to draw it, it would create a sphere. The center of that sphere in this case is where I've put the capital C. This is known as the center of curvature of that spherical mirror. Naturally, the radius of curvature of that mirror is then simply the radius of that resulting full sphere. What I have labeled small r in this picture, the distance from the center to the actual mirror. There is also another important point known as the focal point. The focal point is simply the point halfway between the center of curvature capital C and the actual mirror. Likewise, the distance from that focal point to the mirror is known as the focal length small f. As you can see in this case, I have placed the object between the center of curvature and the focal point. This will be important as we shall see shortly. Again, as with the mirror, in order to create the resulting image, allow me to draw two light rays that go from the object to the mirror. As this is now a spherical mirror, it is more difficult to see what is going to happen to the light rays as they strike the mirror. However, in this diagram, there are several light rays we can look at which simplify things. One such light ray is one that goes from the top of the object through the focal point. Such a light ray, when hitting the mirror, gets reflected horizontally as I have shown. In the opposite sense, another similar light ray is one that is instead incident on the mirror horizontally. Once reflected, this reflected light ray then heads towards the focal point, as I have again shown here. Now that we have again two reflected rays, we can see where they meet up and create the image. As you can see here, they instead meet up on the left. They instead meet up in the actual medium, and therefore the resulting image will be real. What is the actual size of that image? Remember, with the plane mirror case, I only considered a point. Now I'm considering an actual 2D object represented by a vertical arrow, and therefore I expect to also get a 2D object. Well, as I took the simple case of having the bottom of that object halfway through the mirror, this means that the bottom of the resulting image will also be placed along the line halfway through the mirror. Therefore, the resulting image of the object is as I've shown here. It goes from that horizontal line to where the two light rays meet. As you can see here, there are two neat results about this image. Firstly, as I already stated, this image is real. It is created by light rays actually meeting up, actually crossing each other, thereby creating a real image to the left of the mirror. Also notice, and this is one of the benefits of representing the object by an arrow, that that arrow has now flipped. It is upside down, and therefore the object is said to be inverted. If we looked at that image in that spherical mirror, we would see that object upside down. For example, if that object was originally a chair, if we looked at that chair through the mirror, we would see that chair upside down. We would see the image inverted. Unfortunately, things get a bit more complicated. In the case of plane mirrors, the image was always virtual, independent upon where the object was placed in relation to the mirror. For concave spherical mirrors, however, there are two different possibilities depending on where the object is placed. In this example, I have placed the object between the center of curvature and the focal point. If I instead place the object to the right of the focal point, we instead get a different result. Again, allow me to draw the exact same two light rays I did in the previous diagram. The first light ray goes horizontally from the object and then through the focal point as I've shown here, and the second initially goes through the focal point and then ends up horizontally. Of course, as the object is to the right of the focal point, if I wish the light ray that is incident on the mirror to go through the focal point before going through the mirror, I must draw a dashed line from the focal point to the object as I've shown here. In this case, where do these two reflected light rays meet? Hopefully it is clear that these two reflected rays are diverging to the left of the mirror. That means that these two light rays must instead meet virtually to the right of the mirror, as I've shown here. Again, as I've simplified things by putting the bottom of the object on the line that goes through the halfway point of the mirror, the bottom of this image will also be on that line. Therefore, the resulting image is as I've shown here. Here we see in a sense that we get the opposite result that we got the last time. Rather than getting a real image, we now have a virtual image, and rather than getting an inverted image, we now get an upright image. These two results are in fact true in general for concave mirrors. For an object that is placed between the center of curvature and the focal point, we always get a virtual inverted image. For an object that is instead placed to the right of the focal point, we instead always get a virtual upright image. To finish off, I will leave it to you to see what happens at the point in between. What is the resulting image for an object that is actually placed on the focal point of the mirror? Next, I would like to consider the other type of spherical mirror, namely a convex mirror. As I already stated, a convex mirror is, if you like, a concave mirror that is turned 180 degrees, as I've shown here. As this mirror is now curving, if you like, to the right, both the center of curvature and the focal point are in a sense virtual. They are behind the mirror on the right as I've drawn here. Let us now consider where and what is the orientation of an image for a convex mirror. Of course, the actual object has to be to the left of the mirror, and as we have no interesting points on the left, I'm going to place the object randomly as I've shown here. However, again, to simplify things, I have the bottom of the object placed on the horizontal line that goes through the center of the mirror. Let us again consider two light rays that are reflected off the top of the object towards the mirror. Again, looking at the same two light rays, the first being a horizontal light ray and one that heads towards the focal point. For the horizontal light ray, the reflected ray will go through the focal point. As it is a reflected ray, it of course must stay on the left, and since the focal point is on the right, we instead represent that by a dashed line as I've shown here. For the incident light ray that goes towards the focal point, it of course for the same reasoning cannot actually go through the focal point since it is on the right, so again we draw a dashed line as I've shown. This light ray, as before, creates a horizontal reflected ray as shown. In this case, where do these two reflected rays meet? Well, again, I hope it is obvious that these two reflected rays are divergent to the left of the mirror. They instead meet virtually to the right of the mirror as shown here. Therefore, again, as the bottom of the object is on this horizontal blue line, the resulting image is as shown. This means that in this case, the resulting image is both virtual and upright. In fact, unlike concave mirrors, for convex mirrors this is always true. It is always the case that the resulting image is virtual and upright. There is no second possibility like there is with concave mirrors. In the examples of both concave and convex mirrors, I have demonstrated how we can determine if the resulting image is real or virtual and upright or inverted. However, I have not shown how we determine how far the image is from the mirror and what its actual size is. If you look back at these diagrams, you will see that the resulting images are not necessarily the same distance from the mirror as that of the object, and you will also see that the size of the images are different than the objects. The black arrows representing the object are different lengths to that of the black arrows representing the images. These distances and sizes are instead calculated using two different equations that I will show here. The first equation is known as the thin lens equation, as it is used primarily in lenses, which we will talk about later. Let us assume that we have either a convex or concave spherical mirror of focal length small f. Let us also assume that we place an object a distance u from that mirror. The resulting distance of the image, what I will call v, from that mirror is given by this thin lens equation. 1 over u, in other words 1 over the distance the object is from the mirror, plus 1 over v, in other words the distance the image is from the mirror, is equal to 1 over the mirror's focal length f. Remember also what the focal length is defined as. The focal length is simply half the radius of curvature. This is important to know, as in the MCAT you may instead be told the radius of curvature and perhaps u and be asked to find v. We must also be very careful with what the signs are of these three quantities. Firstly, u is always positive. This is because the object is always placed in the real world to the left of the mirror. Therefore, the value of u is always taken to be plus. V, the distance from the image to the mirror, can be plus or minus depending upon whether the image is real or virtual. If the image is real, which can be the case only for a concave mirror, then this value of V is positive, it is a plus. If the image is instead virtual, which is always the case for a convex mirror and sometimes the case for a concave mirror, then the value of V will be negative. Finally, the sign of the focal length is dependent upon what type of spherical mirror we are using. If the spherical mirror is a concave mirror, then that focal length is positive. This is because, if you like, the focal point of that mirror is to the left of the mirror and therefore real. Contrary to this, the focal point for a convex mirror is to the right of the mirror and therefore virtual, and therefore the focal length for a convex mirror is negative. We of course have provided many examples of using this equation in the sample passages. This equation tells us information about where the image is placed, but it does not tell us anything about the size of the image. That is, whether the image is the same size of the object or whether it has got bigger or smaller. This is instead done by using the equation associated with magnification. The magnification m of an image is given as follows. It is simply equal to minus v over u, where v and u have the same meanings as they did in the thin lens equation. Therefore, on the MCAT, it is not uncommon to have to calculate v from the thin lens equation and then use that v in this equation about magnification to calculate the size of the resulting image. As with the thin lens equation, here we also have to be careful about signs. I have already defined what signs u and v have to be in the thin lens equation, and those signs stay the same here. What matters here instead is, what does the resulting sign mean for m? In other words, if we calculate what minus v over u is, and we get, for example, minus 7, what does that negative sign actually mean? What does m equal to minus 7 mean? Having a negative magnification means that that image is inverted. Therefore, a magnification of minus 7 means that the image is inverted and 7 times the length of the original object. If we instead got m is plus 7, that means the image is upright and is 7 times greater than the object. We of course can also get m being less than 1, and therefore the size of the image will be less than the size of the object. Up to this point, we have only considered light rays that are reflected. That is, light that is propagating through one medium, incident upon a boundary between that medium and another medium, and then reflected back into that same medium. However, depending upon the medium, light rays can also pass from one medium into another medium. When doing so, light rays undergo what is known as refraction. For example, as I'm sure you've seen, if you are standing in a shallow swimming pool, then you are able to see your legs, albeit a bit distorted. This must mean that light rays can travel from air into water. Likewise, many people wear eyeglasses. Light must be able to pass from the medium of air through the medium of glass. Anytime light travels from one medium into another medium, it undergoes what is known as refraction. Simply put, as light goes from one medium into another, that light ray is bent. The direction of the light ray changes. This is refraction. The amount by which a light ray is refracted as it goes from one medium into another is determined by what is known as the law of refraction, or Snell's law. To see this in action, again, let's consider a simple situation. Let's assume we have a medium on the bottom, medium 1, and a different medium on the top, medium 2. For example, medium 1 could be air and medium 2 could be water. As in the case with the law of reflection, I will include a normal to the boundary between both media. It is important to remember for the MCAT that any angles associated with both reflection and refraction are defined relative to the normal and not to the boundary between the two media. Also recall that I stated that the speed of light in a particular media stays the same. For example, in a vacuum, the speed of light is roughly 3 multiplied by 10 to the 8 meters per second. Also, on the MCAT, you may assume that this is also the speed of light in air. However, you may not assume that this is the speed of light in other media. For example, in water, the speed of light is bigger by approximately a factor of 1.3. To quantify different speeds of light in different media, we introduce what is known as the index of refraction n. The index of refraction for a particular medium is simply equal to the speed of light in a vacuum divided by the speed of light in that medium. In other words, c, that 3 multiplied by 10 to the 8 meters per second, divided by whatever the speed of light is in the medium. As I just said, the speed of light in water is roughly 1.3 times greater than that in a vacuum. Therefore, the index of refraction for water is roughly 1.3. However, for a vacuum, and as you may assume for air on the MCAT, the index of refraction for both a vacuum and air is 1, since c is simply equal to v. Why have I introduced this now? Well, it turns out that this index of refraction comes into the law of refraction. To see this, let us consider a light ray that is incident on the boundary between the two media. As we are looking at refraction here, this light ray will now enter the second medium, but with a different direction due to undergoing refraction. Let us define θ1 as the angle of incidence, in other words, the angle between the incident ray and the normal, and θ2 as the refracted angle, the angle between the refracted ray and that same normal. Let us also assume that medium 1 has an index of refraction n1 and medium 2 has an index of refraction n2. The law of refraction, in other words, Snell's law, says the following. The index of refraction in medium 1 n sub 1 multiplied by the sine of the incident angle θ1 is equal to the index of refraction in medium 2 n sub 2 multiplied by the sine of the refracted angle θ2. As you can see, this equation is considerably more complicated than that of the law of reflection. As such, let's look at it in more detail. Hopefully it is clear from this equation that when light goes from a medium with an index of refraction n sub 1 into a medium with a higher index of refraction n sub 2, then sine of θ2 must be less than sine of θ1, and therefore the light ray will bend towards the normal. That is, θ2 will be less than θ1. This is the case when light goes from air to water. Remember, the index of refraction of air can be assumed to be 1, and the index of refraction of water is roughly 1.3. Therefore, as the light ray travels into a medium that has a higher refractive index, the light ray will be bent towards the normal in that medium. When light travels from a medium with a high refractive index into a medium with a lower refractive index, the light ray will bend away from the normal. I encourage you in your own time to try different experiments at home to see if Snell's law holds up. For example, you can place an object like a pencil into a cup of water or other liquids. You should see by looking into the water that that pencil seems to bend at the boundary. See if you can work out before doing so whether you expect that pencil to bend towards or away from the normal. As I just stated, when light travels from a medium of high refractive index to a medium of low refractive index, that light ray in the second medium will bend away from the normal. Therefore, it makes sense to think about the possibility that there is some incident angle above which the light ray will not enter the second medium at all. To see this, let us draw a quick diagram. Here below this boundary, the blue line, I have a medium with a high refractive index, for example, water. Above this boundary, I have a different medium with a lower refractive index, for example, air. As we now know, an incident light ray, as I have drawn here, in this case it will be bent away from the vertical as I have shown here. If we make that incident angle even bigger, then after passing the boundary, that light ray will be bent even more away from this normal, away from the vertical. Therefore, there must be some incident angle, which I've called the critical angle θc, at which that refracted light ray will travel along the boundary. Any incident angle above this critical angle will result in light rays that instead pass back into medium 1. This is the phenomenon known as total internal reflection. What is this critical angle θc? Well, we can calculate it using Snell's law. Remember, Snell's law states that the refractive index in medium 1 n sub 1 multiplied by sine of the incident angle, in this case the incident angle is the critical angle theta c, is equal to the refractive index in medium 2 n sub 2 multiplied by the sine of the refracted angle. What is the refractive angle when the incident angle is equal to the critical angle, in other words in that third light ray that I have drawn? Well, I hope it's clear that the angle between the refracted ray and that normal, the vertical line, is 90 degrees. Therefore, the refracted angle theta 2 is simply 90 degrees. Of course, sine of 90 degrees is equal to 1, and therefore this equation can easily be rearranged for the critical angle theta c. Doing so, we get that the critical angle theta c is equal to the inverse sine of the refractive index of medium 2 divided by the refractive index of medium 1. Therefore, we see that the critical angle is purely dependent upon what the refractive indices are of both media. Any incident light ray that has an incident angle greater than the critical angle will not enter the second medium. It will instead undergo total internal reflection and remain in the first medium. One application of light refraction is that of lenses. Lenses allow light to propagate from left to right while also changing the direction of the light rays. Lenses can be seen in, for example, telescopes, and perhaps more well known to you in glasses. Light travels from a source, for example the sun, through glasses into our eyes. These glasses act as lenses, allowing light to pass through them while also changing the light ray's direction. It is important to note here that light goes through many stages, going from that source through the glasses to your eye. That is because light rays are in fact refracted twice here. Light rays are refracted going from the air into your glasses into the lens, but also the light rays then leave the glasses, leave the lens, and go back into the air, thereby getting refracted again. However, on the MCAT, you may assume that all lenses are infinitely thin. That is, they have a negligible thickness. Therefore, instead of a light ray being refracted twice, instead you may assume that a light ray is only refracted once in the middle of a lens. To see this, just like mirrors, let us look at the two different types of lenses, convex and concave lenses. This first lens that I have drawn is an example of a convex lens. Note that the light rays for a lens in a sense do the opposite of what they do for a mirror of the same type. For a convex lens, the light rays converge, as I've shown here. Remember, for a convex mirror, the light rays instead diverged. Note here also that I've used the thin lens approximation. Each light ray should of course be refracted twice, when going from air into the lens and then going from the lens back into the air. Instead, I've made this approximation and I only have the refraction happening once in the middle of the lens. This is done as it will make it easier to work out where the resulting images are when we look at such diagrams. Likewise, this is an example of a concave lens. Again, unlike a concave mirror, the light rays are diverging. After the incident light rays pass through the lens, they then diverge and spread out. You may also recall when we looked at mirrors that one of the equations was known as the thin lens equation. This is because when it comes to lenses, this equation can also be used, but only if we make this approximation that the lens has a negligible thickness. In fact, it turns out that we can use both equations that we used with mirrors. 1 over u plus 1 over v is equal to 1 over f, and the magnification is equal to minus v over u. Also, as with mirrors, I will now look at concave and convex mirrors separately and explain what these quantities mean in terms of lenses. To begin, let us consider a concave lens, a lens which causes the incident light to diverge. We can again consider quantities related to the lens like we did with the mirrors. For example, we can again consider the focal point of a lens. The focal point, remember, is simply the point that is halfway between the center of curvature and the mirror or lens. Of course, in the case of a lens, we have two different curved surfaces. The left-hand side and the right-hand side of a lens are both curved. Therefore, we in fact have a focal point an equal distance from the lens on both the left and the right of the lens. Here I have just drawn the focal point on the left as it turns out, it is the only point we will need in order to create the image. Again, let us assume that we have an object to the left of the lens. Here I have drawn that object to the left of the focal point. As in the case with mirrors, we assume that the bottom of that object is on the horizontal line that goes through the middle of the lens. Let us also again look at two different light rays that emerge or are reflected from the top of the object. The first light ray is incident on the lens horizontally. As in the case with mirrors, the refracted light ray will pass through the focal point of the lens. However, remember there are two different focal points associated with the lens, one on the left and one on the right. However, we also know that a concave lens causes light to diverge. Therefore, that refracted light ray cannot go through the focal point on the right. It can only be associated with the focal point on the left. That is because we expect this light ray to travel to the top right. What in this case we do is we draw a dashed line back towards the focal point to determine the direction of this refracted ray. In the case of lenses, the second light ray is even easier to draw. It turns out that a light ray that goes through the exact center of a lens continues on without changing direction. Therefore, we simply draw a line from the top of the object through the middle of the lens, continuing in the same direction. As expected, we have two light rays on the right which are diverging. We can now ask, where do these light rays meet, creating the resulting image? As these light rays are diverging, these rays will never meet. Therefore, the resulting image must be virtual. We have to draw light rays backwards to the left, where they would instead hypothetically meet. Again, the bottom of this image will be on that horizontal line, and therefore the resulting image is as I've shown. Here we see that the resulting image is virtual because we had to extend hypothetical light rays backwards, and upright as the arrow representing the image is in the same direction as the object. In fact, it turns out, and I encourage you to check this by trying different situations, that the images created by concave lenses are always virtual and upright, regardless of where the object is placed in relation to the lens. Let us now check what the resulting image is for a convex lens. Remember, a convex lens is one in which the light rays instead converge. That is, they approach each other after passing through the lens. Again, I've drawn the object, the lens, and the horizontal line passing through the center of the lens. Here again, I have labeled the focal point, and I have labeled the focal point on either side, as this time we're going to need the focal point on the right. In this case, as with the example with the concave lens, I've placed the object to the left of the left focal point. Let us again consider the same light rays we did with the last lens. Again, we have a light ray that travels from the top of the object horizontally towards the lens. As with all of these horizontal incident light rays, the refracted ray must pass through a focal point. As we know for convex lenses that light rays converge, we expect the refracted ray to travel towards the bottom right. Therefore, this light ray must pass through the focal point on the right, as I've shown here. Again, as in the case for the concave lens, the second light ray simply goes from the top of the object through the center of the lens, continuing on in the same direction. Again, we can ask, where is the resulting image? That is, where do these light rays meet? Where do they intersect? Here it is pretty clear that they intersect on the right, as I have shown here. Again, the bottom of the image must be on this horizontal blue line, and therefore the resulting image is as I've shown here. As we see in this case for a convex lens, the resulting image is real as it involves actual light rays intersecting, and it is inverted. Instead of getting the up arrow that represented the object, we now have a down arrow. The image has been inverted. Unfortunately, just like for a concave mirror, a convex lens has different results depending upon where the object is placed relative to the lens. To see this, let us construct a similar diagram, this time with the object to the right of the focal point on the left. Again, let us draw the same two light rays. The first light ray travels horizontally to the lens, resulting in a refracted ray which travels through the focal point on the right. Also again for the other light ray, we draw a light ray that goes from the top of the object through the middle of the lens and continuing on in the same direction. It may perhaps not be very clear from this diagram as it appears the light rays are kind of parallel on the right, but they in fact should be diverging. This means that the light rays will only intersect if we extend these light rays hypothetically to the left as I've shown here. This means that the image is created to the left as I have shown here. Therefore, in this case, with the object placed to the right of the left focal point, we get that the image is virtual because we needed to extend hypothetical light rays, and it is upright. The arrow representing the object is in the same direction as the image. Just like in the case with concave mirrors, these are the only two possibilities. If the object is placed to the left of the left focal point, the resulting image is real and inverted, and instead, if it is placed to the right of the left focal point, the resulting image is instead virtual and upright. As I also stated, we can use the same equations that we use for mirrors for lenses. Again, however, let's be careful with sign convention. As in the case with mirrors, the distance from the object to the lens is always positive. This is because the object can always be considered to be real. The value of v, that is the distance from the lens to the image, is positive if the image is on the opposite side to that of the object. In other words, for all the examples I have shown you, v is positive if the image is to the right of the lens. Conversely, v is negative if the image is on the same side as the object. In other words, on the left in all of my examples. Finally, and be careful you don't make this mistake on the MCAT, the focal length was positive for a concave mirror, but is instead positive for a convex lens. Likewise, the focal length is negative for a convex mirror, but positive for a concave lens. We have provided many examples in the sample passages that check to make sure that you understand the sign conventions for both mirrors and lenses. Next, I would like to briefly mention what is known as the power of a lens. The power of a lens, if you like, is a measure of how much a lens changes the direction of light rays. That is, a lens that has a high power causes a very large change in the direction of the light rays. The power of a lens can be calculated simply as follows. The power capital P is simply equal to the inverse of the focal length. In other words, capital P is equal to 1 over F. Therefore, as the focal length is measured in meters, the power is measured in per meters. Again, to save time so that we don't have to write per meter all the time, we define a per meter as a diopter. 1 diopter is equal to 1 per meter. Again, if you have very bad eyesight, then the glasses you need to wear will have a very large power compared to glasses worn by someone who has slightly bad eyesight. We can also consider more complicated situations involving multiple lenses, and this is something you do need to know for the MCAT. For example, as I've shown here, we can have light passing through a concave lens, after which it passes through another concave lens. We can then ask what is the total magnification of the system, the total power of the system, and so on. Such a system behaves as a single lens with an equivalent focal length f as follows. The inverse of that equivalent focal length is equal to the sum of the inverses of each individual focal length. In other words, 1 over the equivalent focal length is equal to 1 over the focal length of the first lens plus 1 over the focal length of the second lens, and so on. Since power is simply equal to the inverse of focal length, the equivalent power of the system can be calculated even more easily. The equivalent power capital P is simply equal to the power of the first lens P1 plus the power of the second lens P2, and so on. Finally, we can also talk about the magnification of the system. Naturally, as the light passes from one lens to another, the size of the image after the first lens will be different from the size of the object. The size of the image in the second lens will then also be changed from the size of the image from the first lens, and so on. In fact, the total magnification of the system is equal to the product of the magnifications of each individual lens. In other words, the equivalent magnification M is equal to the magnification of lens 1 multiplied by the magnification of lens 2, and so on. We have provided an example of such a multiple lens system in a sample passage, and I encourage you to check it out, as I would consider it on the level of the most difficult passage you could get on the MCAT. Unfortunately, both mirrors and lenses are not perfect. When reflecting and refracting light rays, they do not focus the light rays correctly, therefore causing distortions in the image. Two such examples of errors or aberrations need to be known for the MCAT. The first type is known as spherical aberration. Spherical aberration is caused by parallel rays that are not perfectly reflected at a mirror or refracted through a lens, particularly at the edge of a lens or the edge of a mirror. As you can see here, I have many parallel rays incident on a lens, but as we get further from the center of the lens, the incident rays are refracted more than we would like. Ideally, we would like all of these parallel rays to focus at one point. However, as we get further from the center of the lens, the light waves get refracted more than we would like. This causes a spread out of the refracted rays, resulting in a blurry image. The second type of aberration you need to know for the MCAT is what is known as chromatic aberration. It turns out that the amount by which a light wave is refracted is dependent upon the wavelength of the light. Since the color of light purely depends on its wavelength, different light colors when traveling from one medium to another will be refracted by different amounts. This is what is known as dispersion of light. This therefore means that if we have light rays composed of various different wavelengths and therefore different colors, traveling parallel to each other, once they are incident on a lens, they will be refracted by different amounts. This is, for example, what happens when white light is shone on a prism. White light is light that is composed of many different wavelengths, and therefore many different colors, and therefore when it hits and passes through the prism, those different wavelengths, those different colors are refracted by different amounts, thereby creating the many different colors that are seen. As we see here for a lens, this causes incident light rays, which are composed of many different wavelengths, to refract by different amounts. This will result in a rainbow halo around the image. In the real world, this type of aberration is corrected in, for example, eyeglasses by using a special coating. This coating has a different dispersive quality to that of the lens itself, thereby reducing the effect of chromatic aberration. This now completes our two-part series about light. With regards to geometrical optics, as you may figure, it is very difficult to show a question without having first a lot of detail, for example, like a passage. Therefore, the questions I presented here are very simple in nature. More complicated questions can be seen in the sample passages we have provided for you. For example, the passage that I already mentioned about a multiple lens system. The first question I have here, though, is testing our knowledge about the resulting images through a lens. For a concave lens, what type of image is produced? Is it both real and upright? Is it virtual and upright? Is it real and inverted? Or is it virtual and inverted? To answer this question on the MCAT, Rather than simply memorizing what the result is, I encourage you to simply draw a quick diagram. As we are told a concave lens always produces something in the question, we know we only have to draw one diagram. You can therefore quickly draw a concave lens, an object to the left placed anywhere, then draw two light rays coming from the top of the object through the lens, and see what happens to those light rays. You will see that the resulting image created will be virtual and upright. Therefore, the correct answer is option B. This next simple question is making sure we understand what is meant by the index of refraction. We are asked, when is the index of refraction equal to 1? Is it in a vacuum, in air, in water, or is it never the case that the index of refraction is 1? Well, let us recall how we define the index of refraction. The index of refraction n for a medium is simply equal to the speed of light in a vacuum c divided by the speed of light in that medium v. Therefore, straight away, we can see that this index of refraction n will be 1 when c is equal to v. In other words, when the speed of light in a vacuum is equal to the speed of light in that medium. Therefore, clearly, the medium must be that of a vacuum. Therefore, the correct answer is option A. Of course, for the MCAT, you may also assume that the index of refraction for air is 1, but this is not precisely true. More precisely, the index of refraction for air is roughly 1.0003. Therefore, although you may assume when answering questions about light propagating through air that n is equal to 1, it is not exactly the case, and therefore the only correct answer to this question is option A. Finally, this question has to do with a multiple lens system. Again, as I stressed, there is a much more complicated series of questions relating to a passage on multiple lens systems in one of the samples we have provided. This question instead simply asks, what is the equivalent magnification of a multiple lens system? Is it the sum of each individual magnification? Is it the product of each individual magnification? Is the inverse of the equivalent magnification equal to the sum of the inverses of each individual magnification? Or is the inverse of the equivalent magnification equal to the product of each individual magnification? Well, remember, for a multiple lens system, there are three different equations you need to know. The equivalent focal length f is determined by 1 over f is equal to 1 over f1 plus 1 over f2 and so on. Since lens power is defined as 1 over f, the equivalent power is simply equal to the power of lens 1 plus the power of lens 2 and so on. And finally, the equivalent magnification of the system M is equal to the product of each individual magnification. In other words, M is equal to M sub 1 multiplied by M sub 2 and so on. Thus, the correct answer to this question is option B. As always, let us now wrap up this video by summarizing what we learned. I emphasized that when light propagates through one medium and is incident upon the boundary to another medium, one of two things can happen. Either that light is reflected at that boundary, staying in that same medium, or the light is refracted into the second medium, changing direction in the process. In general, some light rays are reflected and some are refracted. How much is reflected and refracted depends upon what the two media are. If the light is reflected, then we know it must follow the law of reflection. That is, the incident angle is equal to the reflected angle. We also know that for the case of plane mirrors, the resulting images of such reflected light is always virtual. That is, the image is always behind the mirror. For concave spherical mirrors, we instead know that two different types of images can be created depending upon where the object is placed in relation to the mirror. Either real inverted images are created or virtual upright images. Instead, for a convex mirror, virtual upright images are always created. I then introduced two equations, the thin lens equation and the magnification equation, that allowed us to calculate where that image is placed and the size of the image. I emphasized that it is important to remember what the signs of each of these quantities are depending upon the situation. The second thing that can happen to light rays when incident upon another medium is that they are refracted into that medium, thereby changing their direction. The resulting change in direction of the light rays is fully governed by what is known as Snell's law. Snell's law tells us that the amount by which the light ray is refracted is dependent upon the incident angle and the indices of refraction of both media. It is also important to remember that the angles in both reflection and refraction are defined relative to the normal. They are not defined relative to the boundary between the two media. This is a very common mistake that many students make on the MCAT, so please ensure that you understand this. Based on the form of Snell's law, it is clear that for light that is incident above a certain critical angle, that light will not enter the second medium but will instead be reflected. This is known as total internal reflection. Similar to reflection by mirrors, I then looked at refraction by lenses. Of course, as a lens is composed of its own medium, as light travels through a lens, it in general gets refracted twice. For example, light going through reading glasses passes from air to the glass and then back from the glass to air. Therefore, it must get refracted twice. However, on the MCAT, we use the thin lens approximation. We assume that the lens has negligible thickness. In doing so, we instead approximate that the light ray is only refracted once in the middle of the lens. Again, we do this because it makes it easier to draw light ray diagrams, thereby determining the position of the image. As was the case with convex mirrors, concave lenses always produce the same type of image independent upon where the object is placed in relation to the lens. Concave lenses always produce virtual upright images. Convex lenses, on the other hand, create two different types of images dependent upon where the object is placed in relation to the lens. They can either create real inverted images or virtual upright images. I then talked about the idea of lens power, which is a measure of how much the lens changes the direction of the light. It is defined as simply the inverse of the focal length and has units of per meter, which we call a diopter. I then briefly discussed that in the MCAT you must also be able to deal with a multiple lens system and encourage you to check the sample passage we have provided for you on such a system. I then finished this video by stating that unfortunately, in general, both lenses and mirrors are not perfect at focusing light. Two reasons for this must be known for the MCAT. The first one is known as spherical aberration and is due to the fact that light gets reflected or refracted more as we approach the edge of a lens or a mirror. The second type of aberration, known as chromatic aberration, is due to the fact that light of different wavelengths is refracted by different amounts. This is what causes the phenomenon known as dispersion, that is, the breaking up of white light into different colours as it passes from one medium into another. This now finishes our discussion on light. We will finish this series with the next two videos on atomic and nuclear physics. In both cases, it turns out that light plays an important role. Therefore, before moving on to these last two videos, please ensure that you are comfortable dealing with the topics that I presented with you so far about light. As always, I hope this video has been useful to you, and I shall see you guys in the next one.